In this section, 5.2, we'll focus on some applications of maximum and minima. How do we use the first derivative test that we've learned and set up in the previous two videos in the previous section, and how do we apply it in the context of, let's say, maximum revenue or minimum cost. I recommend before watching this video, go ahead and read these examples 1 through 4, and they're definitely going to help you set up and figure out what we're talking about. And I'm talking about Wiener-Constantinople, the text that we have in the class. So let's talk about number 9 to start with on page 392. A lot of the problems we deal with the area, perimeter, so let's take a look at this one. So let's say a rectangle has perimeter 20. To have the largest area, what dimensions should it have? For a lot of these problems, I think it helps if you draw the problem. I usually use X and Y for length and width. We can switch them just because we're used to them. And I typically try to solve for Y in terms of X again, so we're using a familiar variable. So you may recall the perimeter. If you walk around the outside of the rectangle, it has two widths, 2x, and then two lengths, 2y equals to 20. And we need to find the area in terms of the two variables, which is x times y. But notice we cannot take the derivative of the area to find the maximum yet. Typically we have to solve for one of the variables using a different equation, which is why we have the perimeter. So if we solve for y, just because it's easier to substitute for y to have it in terms of x. So note we have negative x plus 10. Then we can substitute into the area. So x times y becomes x times negative x plus 10. And we have a quadratic, notice negative x squared plus 10x. It would have a maximum because it's an upside down quadratic. So how do we find the largest area? So we can start by finding critical points. That's from the previous section. Typically stationary, but we can check for other points also. So we find the derivative, which is negative 2x plus 10. Let's set it equal to 0. There are going to be no singular points because it's always defined, no endpoints either. But we can solve. So we have x equals 5. Remember, it's just a critical point. So far, it's just a candidate for maximum. So what we should do is set it up on the number line to plug in into the derivative, a prime. So I picked something relatively easy, 4 and 6 on the other side of 5. And I plugged in 4 into negative 2x plus 10. So you get negative 8 plus 10, which is positive 2. So it's positive. And if we plug in 6, we get negative 12 plus 10. So that's negative 2, and that's negative. And so if you notice, the function is rising, and then it's decreasing. So we do have a maximum at that point. So it's good to check. And since the question asked for dimensions, we have the x, which is the width. We can plug in back into the y to find the length, which is negative 5 plus 10. So we have a 5 by 5 rectangle, which is actually a square. A lot of times, if you just have a simple rectangle, typically the largest area would be a square. That's kind of interesting how it works out. So 5 by 5 feet or whatever the dimensions were. Now let's take a look at some business applications. Assume in number 11 that it costs Apple approximately, and we have this cost set up, 22,500 plus 100x plus 0.01x squared. Let's see, what is x? Dollars to manufacture x 32 gigabytes iPods per day. How many iPods should be manufactured in order to minimize the average cost of an iPod? What is the resulting average cost? So if you recall from previous sections, here we have the total cost. How do we find average cost? We have to do something first. We have to divide the whole equation by x. So if we simplify the constant, 22,500 over x plus 100x over x, which is just 100, plus 0.01x squared divided by x just gives us 0.01x. And we can also rewrite, bring the x from denominator, make it negative exponent, so it could be easier to take the derivative. So that's our average cost equation. Make sure to simplify it first, just because it's easier to take derivative of. So what's the derivative? So I think it's called marginal average cost, or marginal derivative of the average cost, which is negative 22,500, x to the negative second power, plus 0.01. just by itself, and the constant is gone. Once again, we can set it equal to 0. We do not have to worry about the singular points. The derivative is not defined when x equals 0, but then neither is original, and it doesn't make sense to have cost for 0 iPods anyways. So we set it equal to 0 to find stationary points, and we do need to solve typically. So how I solved is we can move 0.01 to the other side and then multiply by negative x squared, which is how I got to the next step. And then you can divide by negative 0.01. So we actually end up with 2,250,000, and that's x squared. Take the square root. So we have positive 1,500. Notice if you take a square root, typically you get positive and a negative. But since we're talking about applications or the number of iPods, the negative doesn't really matter. So we'll just take the positive value. And again, remember that's just a critical point. We gotta test it to make sure it's a minimum. So put it on the number line, pick a couple of easy points. I picked 1,000 or 2,000. I don't think it really matters because we gotta plug it back into the original. It's actually this one, negative 22,500 over x squared plus 0.01. Probably you would do this by calculator, but still, if you plug in 1,000, I think you get a negative small decimal probably, but you get a negative value. If you plug in 2,000, I think you get a small positive decimal. So you can check with your calculator, but we do get a minimum at that point. And again, whatever the question asked, so we were asked for how many iPods would minimize the average cost per iPod. That's 1,500 of them. But also we need to find the resulting average cost, which is the Y value. So if you recall, you can plug in 1,500 into the original average cost. So this is right here. This is the one you want to plug in, 22,500 over x plus 100 plus 0.01x. So if you plug that in using calculator, I think you get $130 per iPod. So that's the average cost. So that's just the typical example of minimize a cost, or in this case, average cost. Now, here's one about controlling emissions. I think we talked about that a little bit in previous chapter, I believe section 4.2. But here we have the cost again of controlling emissions, this time in terms of quantity of emissions. So if we have C of Q equals to 4,000 plus 100 Q squared, where Q is the reduction in emissions in pounds of pollutants per day, and C is the daily cost of the firm in dollars of this reduction. What level of reduction corresponds to the lowest average cost of pollutant, and what would be the resulting average cost to the nearest dollar? So if you note, it's very similar as previous problem. If you read through it, so you got to find the average cost, divide the cost by Q. It's a very similar problem. And then to find the minimum, we take the derivative of the average cost, which happens to be negative 4,000 Q to the negative second power plus 100. Once again, set it equal to 0. Move the Q squared on the other side. I guess you can move it 100 on the other side first and multiply by negative Q squared. Then divide by 100, actually negative 100, and then we get Q squared equals 40. Do not panic. Sometimes it's not a perfect square root. Here we have square root of 40, but if you round it, we get about 6.32 pounds of pollutants per day. And you can still check it if it's a minimum. Again, I picked two integer values, 6 and 7, just to make it easy, and plug them in into the, before we set it equal to 0. So negative 4,000 over Q squared plus 100, talking about the derivative. So if you plug in 6 squared, that's about 3,600. So I think it's less than 100. So actually, sorry, more than 100. So you get negative value here. But if you plug in 7, you get a smaller fraction, and so you get bigger. Again, check with your calculator. And so you should get a minimum at that point. And I plugged in, I did round here just to make it easier, but I plugged in actually square root of 40 into the original function. If you remember where the average cost was, 4,000 divided by square root of 40 plus 100 times square root of 40. That's what I did. The less you round, the more accurate your answer would be. So rounded to the nearest whole dollar was about $1,265. So about $1,265 per pound of pollutant. So that's what I got in this problem. Now, the next problem, so we'll just kind of jump around the concepts, again, just simply to apply it. This one is another rectangle, but it has the cost involved with it. So, let's say if I would like to create a rectangular vegetable patch. The fencing for the east and west sides is for some reason more expensive, $4 per foot, and the fencing for north and south sides costs $2 per foot, a little bit cheaper. Let's say we have a budget of $80 for this project. What are the dimensions of the vegetable patch with the largest area that I can enclose? So similar to the perimeter problem that we did earlier, but just a little bit more involved. Again, draw it again. I assumed that the width was east and west sides just because it's a little more expensive. Trying to maximize our budget here, I suppose. And again, area is, if you recall, x times y. Again, we have two variables. We need to solve for one of them. So I set up the cost equation just so that it would be easier to solve for y. Again, just strategically placing it. You can always switch your width and length if it doesn't work out that way. But we have $4 times 2 of the widths, which is 2x, plus $2 times 2 of the lengths, which is 2y, equals to 80. And you can simplify the cost. We get 8x plus 4y equals 80. Once again, we can solve for y. Move the x to the other side, negative 8x plus 80. And so we get y equals to negative 2x plus 20 if you divide by 4. And now we can plug it into the area to make it all in terms of x. So we get negative 2x squared plus 20x. Once again, we have an upside down parabola. We have something like this. If we draw it. So we would have a vertex or a maximum right at that point. And so once again, you can take the derivative, which is negative 4x plus 20. Once again, set it equal to 0. Typically, a stationary point only applies. So we get x equals 5. Once again, you can plot it on the number line. You can pick any two. I think I picked 4 and the 6. You can pick any points. But I did get positive switching to negative. So we do get a maximum. I think you can draw it so the function is increasing versus decreasing. Okay, let me try to draw it. Sorry, I had some problem with my pen here, but here, so after the pausing the video, I think I fixed it. So we do get a maximum at this point, and once again, we can plug into the y. This time we get negative 2 times 5 plus 20 equals to 10, so we do not get a square because of the cost, but we get 5 by 10. I think on the homework may ask you to put a smaller first or whatever the directions are, but 5 by 10 vegetable patch, I think it's with feet, gives us the largest area. Now, what if we reverse the situation and what if we'd given the area and we're given the cost, actually similar as in previous problem, but we're given the area and we're trying to minimize the cost. So here we have, for tax reasons, I need to create a rectangular vegetable patch with an area of exactly 242 square feet. And again, the fencing, as in previous problem, for east and west costs $4 per foot, and the fencing for north and south costs only $2 per foot. What are the dimensions of the vegetable patch with the least expensive fence? So if you know it, we're trying to minimize the cost. So now this time we have area, which is 242. We can use it to solve for y. How we can do that? We can divide by x. So I get 242 over x. And if we have the equation as in previous problem, 8x plus 4y, then we get 8x plus 4 times 242 over x. So if you simplify it, we get 8x plus 968 over x, or you can rewrite it with a negative exponent. So note, a rather different problem if you switch them around. Once again, from here on, it's very similar. You can take the derivative, set it equal to 0. And again, I move the 968 over x squared to the other side to make it positive. And we can multiply by x squared on both sides. So we get 8x squared equals to 968. Divide by 8. We get x squared equals 121, which means x equals 11. And once again, you can test it real quick with C prime. Do you get a minimum? I plugged in 10 and 12, and yes, we do. And we can plug into the y to find the length. And here we get 242 over 11, which is 22. So we get an 11 by 22 feet vegetable patch. Okay. Now, what about maximum revenue? We can apply the same idea. What if we have Hercules Films, for example, is deciding on the price of the video release on the film Son of Frankenstein. Its marketing people estimate that at a price of $P, it can sell a total of this quantity, 200,000 minus 10,000 P copies. What price will bring in the greatest revenue? So note, you may have to construct the revenue equation first, which is P times Q, price times quantity. And then, so it's P times, we can plug in for the Q. So we'll actually get 200,000. I think I have an extra 0 here, but to get 200,000 P minus 10,000 P squared. And once again, you could take the derivative and so for P, and so we get P equals to $10. So again, I picked something easy, 5 and 15, to check into the derivative. So if it's 5, we get 200,000 minus 100,000, so it's positive. If it's 15, we get 200,000 minus 300,000, so it's negative. So we do have a maximum. So P equals $10 maximizes the revenue. Okay. Now, what if we need to figure out, I think the most difficult problem in these problems is to come up with an equation sometimes. So the last few examples, maybe I'll make another short video after this one. Actually, I will include the next 3 in the next video, just so that this video is not too long. So the next one we're going to do, what if we find the demand from given some information, and how can we find maximum revenue? So follow up with the next video.